Hello again.
Hey, Becca. How's it going?
Oh, it's good. Just managing the giant Zoom.
Yeah, it's a lot of fun.
Yeah, I'm letting in all the instructors early, but so far you're the only other instructor that's on, so
Nice.
it's just the two of us.
Woo. How's your work going?
It's good. It's been a little on pause just because I've been interning with UNAVCO this summer, but it's starting to ramp up again because abstracts for a volcanology conference are due right after the ISCE meeting. So I've been having to kind of do this and then go and work on the abstract for this conference. So the next 2 weeks are really packed, and then it kind of chills out because then once that's done, the internship's done, the class is done, and then the ISCE meeting's done. So
Awesome. Yeah, it'll be nice to actually do your PhD during your PhD once in a while.
Yeah. How's ASF stuff going?
It's been good. It's a leap to go from, okay, you're a scientist who codes for a bit to, okay, now we consider you a software engineer.
Yeah.
It's been fun to learn all the ways I was coding terribly. But yeah, it's been really cool. It worked out really well. I've been working on my PhD for the last little bit while I'm at ASF, and I'm submitting the thesis this week. So that'll soon be done,
awesome.
and I won't be doing two things at once, which will be great.
Nice. Yeah, you actually can just full-time software engineer.
Yeah.
You can just run all those satellites in Alaska. Hi, Gareth. All right, it's 10, so I will let in people.
Super. We'll just wait a little longer. We have about half the people that we had yesterday so far. I'm sure there's more people waiting to come in. Okay. Still got people coming in. Yeah, in the meantime, there was a question about submitting the homeworks. And it's beneficial if you get them done as close to the normal progression as you can. But we're not going to worry a little bit too much about late submissions, so long as you're done by well, preferably by the end of the course, but in fact the week after the course is also okay. That's when we're actually going to like make sure that things are complete. So if you get a little stuck behind, if you're a little behind, then that's okay. I would say that for the strip map app processing, we do need you to complete that before we look at the Ionosphere notebooks, and I forget what day that is. It's either Wednesday or Thursday. It would be ideal if you have that one done by then. I'll actually check the syllabus right now.
It's Thursday.
Yeah, Thursday morning. So if you can get that the strip map processing done by then, that would be good, because we're going to use that process data to actually generate an ionosphere correction. If you remember looking at the interferogram, they had a bunch of fringes across it that are not like real deformation, but those are actually ionosphere. So in the next exercise with that data, we're going to try and remove the ionosphere. We have a few more people here now. We're up to 60. Maybe this is a good place to start. And the first thing we're going to do today is go over the homework. So really, this is an opportunity to air out your problems. If you had problems or ask questions about what was covered yesterday, I see both Eric and Paul are here now. And that's great. And Forrest is here, sent by France to answer any questions about ASF things. So does anyone have any questions?
At the office hours this morning, Kyra had trouble with getting the error surface plot in the homework to display properly. It seemed like the estimate was reasonable, but the display didn't quite work out. I don't know, Kyra, did you figure that out yet?
Yeah, I think Becca, kind of came up with a solution. My sort of range of variables was super different. So I had like 5 Z values and like 1,000 volume like values or something like that. So it was like stretched weird. But I made those more similar and it looks a lot better.
Okay.
So
Good.
yeah, we figured it out.
Great.
Cool.
There was another question on the NetRC setup that was still a challenge. So I don't know if people are still having questions or issues with that.
Yeah, this is an important one to get straightened out as soon as possible. If so, is anyone experiencing problems with that we can help?
There's at least one person on Slack that found that they had put there's a few characters that if you put them in the NetRC file for your password, they cause problems. So there's a certain, in the 0.7 Cicera thing, it explains about the passwords that you're allowed to use.
Yeah, I remember that dimly from last year, that if you have certain special characters, it doesn't like it.
I remember I used a random password generator and I had to try several times before I got one that worked.
There's a question, will the course from yesterday be uploaded by today? My understanding is that it's been very slow retrieving those files from Zoom. Is that correct, Becca? Do we have an ETA on the upload?
I can ask Melissa and see if she knows, or if she doesn't know, I can ask Scott about that.
She sent us a message yesterday on Slack saying it was taking longer than it had previously, and that's why it's not been done yet. I have a question. Is it possible we can do some steps on GMT-STAR? And the answer is no, because I don't know it. And combine it with ICE? I don't think so. I don't think anyone here has that skill set. Or
No, the file formats are very different. I mean, the basic information is there, but all the metadata and is in a different format. So
it's in a different format. They use different definitions for things like correlation. That's also a point of difference.
And I think the question is, can you take the unwrapped files from GMT-STAR and maybe do time series analysis using, it says ICE here, but I think he means like MinPy. That might be possible.
That's
Does
a
MinPy
Yunjin
support
question.
GMT?
It may be. What I know is that you used to be able to convert freely between GMT and other formats of imagery using GDAL, and they have recently taken out support for the GMT format for some reason from GDAL. So it's much less easy to convert in the way that we might have used to. It's probably quite likely that you could make an interferogram stack that you could import, make a wrapper for MinPy that you could use to import unwrapped interferograms into it. But I'm not sure that capability currently exists.
Yeah, I don't think it currently does, but I'm sure that if that's something people are interested in, we could definitely start working on that together.
Yeah, and there's also no capability to import GeoTIFFs from the Comet LIX system. That's something I've been meaning to write and have not done.
Yeah, that'd be good too.
Yeah, because there's lots of cool data that you could mine from like especially from like the Indian Eurasian collision zone, which I'd like to look at some point without having to process myself.
RA has now processed a large area of Tibet. It's not been transferred to the ASF DAC yet, but it's all been a huge area, like 300,000 interferograms have been processed.
Yeah.
In the last few months.
Looks like Alex has his hand up.
You go, feel free.
Yeah.
Yeah.
Yeah, I just wanted to make a quick note on the Earth Data account. So I had already actually had an Earth Data account, and I didn't see it listed anywhere here, but it took me a while to figure out yesterday. I had to manually enable the ASF like permissions to let it grab the data, and I don't see that anywhere in the documentation that I could see. So I don't know if that needs to get added, or maybe I missed it. But
it should have been.
So there's some information about how you had to accept like the ALOS Sentinel and ALOS permissions, but not.
Yeah, the terms, the user license.
Yeah, but there wasn't anything, I don't think, in here in terms of going into the Earth Data account and enabling the ASF ability to pull the data. But I did it. So in case anyone else is having that problem, I just wanted to.
Where is that setting, Alex?
It's in Earth Data, and then there's like an authorizations menu.
Yeah, I thought we posted a video of Franz doing that.
I may have just not watched the whole video. Then I apologize.
So one thing you
it's
can
at
always,
the end of Franz's video.
yeah.
I'll check.
And one thing you can always try is that when you actually run these things, it will generate URLs for the files it's trying to download. If you click on one of those in the OSL, then it will take you to the, if you haven't got permission, then it will take you to the website and ask you to agree to stuff. And if you do have permission, it will start downloading it to your local machine, which you might not want to do, but it's a good test of whether or not you have the permission set up right.
Got it. Cool. Well, thanks.
Yeah, I think the other thing that Franz was showing is that if you use your Earth Data account to log into the ASF Vertex system, then Vertex checks to see whether you're user licenses have been accepted, and then queries you if to change them if you don't. So that's another good test, is to log into the ASF Vertex system.
Right. So I've done all that, and I think I have all the right permissions set up, but when running that first cell on the strip map app notebook, I'm still getting an error.
Do you want to show us?
Sure. It's this error. And I have my netrc file set up, I think correctly, with my Earth data login. And I don't have any weird characters in my password or anything.
So this error looks like it's not. So this piece of Python code is trying to pull your password out of the netrc file. So it must be something in your netrc file format it's not being able to find the password, username and password.
Okay.
If you go to terminal and you type, rather than showing us your file, if you type wc space .netrc, it'll probably say 0, because it says that the input contains no data.
I mean, this is my netrc file right here. So
Okay.
I have it, but it's.
But what is it at the top level? Is it at your top level?
Yeah, I think so.
Looks like maybe you have some exclamation points in your password. That you have to make a password that doesn't have any exclamation points.
I don't have any.
Pound symbol, is that?
Huh? Oh, okay. It looks like an exclamation point because
Just letters.
yeah. Sorry, the
You're good.
screen was getting pixelated.
And it's the username that it's having trouble with. Your login is an email address and not a username.
It should be a username.
Yeah, try your username.
Let me just check if that's actually my username. I mean, I think I log in with my email. Okay, maybe that's the issue. Maybe I need to.
Yeah, it should be a username. Like mine's just EJ Fielding.
Right. I mean, I think that is my username on ASF.
Oh, and the other thing you can do is put carriage returns in your netrc file.
Just put what? Sorry.
You can put returns in it.
Oh, like a /n or something, or
No, have each thing on a separate line.
oh,
Sometimes.
there's a space there. Maybe that was it.
It doesn't care about spaces.
I don't know why it said no data though. Obviously they stuck it.
Oh, okay, that worked. Weird. Okay.
Yeah, the problem is that on that np.load text call, you're skipping the first row of the text file. So you need to have those carriage returns in between the username.
Let's see. Okay, cool. Thank you.
There's a question in the first 2 lines of the code. Shouldn't we just add the username and the password? Well, you can, but it's better in the long run that you have the netrc file up and working, because then you don't have to do that for every notebook. And so that's our recommended setup.
Also, later when it does, when the ICE strip map app tries to go out and collect the DEM data from the land processes DAC, it's going to look at that same netrc file.
Yeah.
Because it's the same NASA Earth data login.
Which is why we want you to get it set up right now. Because once you have it set up, then everything else is going to work. And in past years, we've had people going into day 3 without it working, and they're just missing out on a whole bunch of content in real time because it's not working.
So maybe we should ask people to raise their hand if they're still having trouble. Just get a feel for how many people are having trouble. So there's 1. 2. That's pretty good if there's only 2 people out of the 75 on 3. Okay, keep them coming.
So do some of those people want live help?
Nate has bike issues, or he's sorting it out. Okay, so anybody else want to just share their screen to show us what the issue is for you?
Data login fails when downloading Alice.
So I know you're having mic problems, Nate, but you could share your screen and show us what you've got, where it's failing.
In the meantime, there's a question: does ICE do SBAS or PS or both? And the answer is no. ICE just processes interferograms, and it can make interferogram stacks. When it comes to doing SBAS, we're going to show you another code called MintPy on Friday that does that.
MintPy does SBAS.
That's what I said.
Yeah. And not PS InSAR.
One can do PS using interferogram stacks and using stamps, but we're not supporting that on this course. I have done it though, a long time ago.
Hey, Gareth, can you hear me?
Yep.
Yeah, sorry, we have a special mic system here. So yeah, I've had Earth Data login for a long time, and it works in the ASF Vertex. And I ran the code with the password lines at the beginning. And I keep getting this error. And I can't tell, maybe it's something with actually my connection that I'm on right now. So I might try on a different network.
Why don't you try clicking on one of those URLs? If you scroll up to like where it actually shows the data file.
Yep.
Not that one, I don't think.
Yep.
But it said you don't have authorization. So like the data.asf, that thing, one of those, yeah.
See, now it's asking for your user license agreement.
This is what when I mentioned that before. This is a great sort of way to figure out if you don't have permission to download something. If you try and click on the URL, don't save it. It'll be a huge file.
Okay.
So yeah, that's the way around, the way to figure those things out.
Okay, cool. So the answer should be in this guy.
Yeah, you should try running that cell again and seeing if it works now that you've agreed.
Yes, there we go. Data.
Yeah, so
Beautiful.
that's the user license agreement that they require for ALOS and Sentinel data from ASF.
Yeah, I checked those boxes in my Earth Data login, but for some reason it didn't take. Cool, thank you.
No problem.
So Muradula, you want to try?
Anyone else wanna? There we go.
Can I speak?
We can hear you, sort of.
I have been trying using the username and password and not netrc file, and now I'm having problem creating it. So you can, in which folder should I create the netrc file?
In your home directory, the top level directory. The one when you open the terminal, that one.
Okay, I'm trying. Thank you.
There's a question in the chat. Are we going to learn time series for InSAR? If you look at the syllabus, we have lectures starting tomorrow about time series, and then we have a whole day devoted to time series exercises on Friday. If I hope you go through the syllabus and see what we're offering, and hopefully you'll like it. Is ICE computationally heavy as compared to other SAR processors, or is it better? I don't know if we've actually done that comparison, but maybe Paul knows if it's better.
I don't know if we can call things better or worse. It is what it is. It's computationally heavy because it's doing a lot of work. Doing a lot of corrections and geocoding and estimation of the ionosphere and that kind of stuff. So there's a lot of functionality built into it.
Right.
ICE includes the focusing software. If you want to use Snap, it does not include any focusing, so you have to start with SLCs.
And if I remember right, it apply well. A lot of things you can turn off manually, but I think GMT-SAR does not do the ESD alignment as a default. So
right,
GMT-SAR might run faster, but it might be less well registered.
I know over at ASF, we've done some comparisons between ICE and Gamma, which is a commercial software for doing this type of processing, and we found them to be pretty similar.
Oh, that's interesting. Good to know.
If you have a powerful computer with GPUs, it's also possible to compile ICE with GPU support and have it run some of the processing steps with GPUs, which can speed it up a lot.
Mm-hmm. The other instructors can correct me if I'm wrong, but I know one of the most computationally heavy steps tends to be unwrapping. And most of the processors use a very similar unwrapping algorithm.
Yeah, GMT-SAR uses Snafu. I think
GPUs don't help with unwrapping, unfortunately. It's the image matching part that is very fast on GPUs.
Yeah,
dense offsets.
ICE3 is a complete rewrite of ICE2, and as a result, it doesn't have anywhere near at the moment the functionality that ICE2 has in it. It's getting close for the basic products. It's all written in C++ instead of a variety of languages, so C++ and Python. In theory, it is a much more uniform, bug-free, and a maintainable set of code, but it doesn't have a lot of the value added, shall we say, functionality, like doesn't have any kind of a stack processor yet. It can't do TOPS processing. It's mostly focused on the ISAR data at the moment, or strip map processing. So there's a lot of things missing that we're hoping over the next year or so before the ISAR launch, either the team itself that's developing it will add, or community will support it and add functionality the way they did for ICE2. But it's a little bit, it's a staged development, and it's a little bit behind where ICE2 is. So I do believe there was a RISAT reader at one time in ICE2. I don't know if it still works. It should be relatively straightforward to make it work. If it's strip map data, it's probably pretty straightforward, especially if it's already processed. It's not raw data. I don't think they distribute raw data. So if it's a strip map based image, you just need the reader and the rest of the software should work. I thought there was, didn't Fuchs put that in at one time, Eric?
A long time ago, I never used it. I never had any RISAT data.
Right, well, now they have several different flavors of RISAT. So RISAT 1, I don't know how easy it is to get access to those data. But in any case, it should be there in some fashion. It may or may not work at the moment, but I think it would be relatively easy to add. And again, ISCE, it's free software. You can download it and modify it yourself. While we're chatting.
Plus you can contribute it back to the repository if you do make a improvement.
Yeah, that's a good point.
So how are those people doing who are trying to update their NetRC files? Can we get a progress report? One positive.
Am I audible?
Who's that?
While we're waiting, I'll just show you. I went to the ISCE repository. I did a grep on RISAT in the Python files, and you can see there is a sensor object for RISAT1. And there is an unpack frame for RISAT. So again, these were added a long time ago. They may or may not be fully functional, but I imagine if the data set hasn't changed, they probably work. And you should be able to do interferometry with RISAT.
If ISRO wants to open some of their data to use for testing, that would help.
Well, I think it is open. If you go to their VEDOS, I think it's either VEDOS or another one of their portals, you can order data. I don't know how easy it is to order it, but I think it's in theory available. And that's how the S-band ISAR data is going to be accessed.
Ah, so that's important to know.
Mm-hmm. Would like to share your screen, go ahead.
What would be the reason for this type of result?
You were showing a latitude, longitude, and height as images. Those should be smoothly varying things, right?
Yes.
So it looks like it could have been right. I didn't see the scales before the screen disappeared. You could show it again.
No, it looked like it was probably correct.
No. Yeah, so what is the issue? These look correct. because those are just images of the latitude and longitude and height as a function of what, range and Doppler?
Yes, this is in the radar coordinates of range and Doppler.
Okay, so you're good. Excellent.
Yeah, when the video is available, you can compare, and I think that's very similar, more the same. Can we have the option to download burst-wise data instead of the entire SLC? That would be a question for our friends at ASF.
We're working on it. No ETA yet, though.
I agree that would
But it's
streamline
something that I know at ASF we consider it really important, and it's one of our priorities to get towards that.
because it would save you a lot of bandwidth, I imagine.
Yes, it would.
Yeah, we'll be talking about that later today. Is the Sentinel-1 TOPS mode is the data is processed in these bursts that are a small subset of the scene. It's about 20 kilometers along track and about 80 kilometers wide. So if you're only looking at a small area, you would be better off just getting a few bursts instead of a whole frame that's 4 gigabytes. Right, and then there's also the situation that the European Space Agency doesn't always use standard frames. But they use slices that vary with time or with satellites. Sometimes the Sentinel-1A data has different slices than Sentinel-1B, and if you're trying to combine them, it's a pain.
So the question about will we be able to do the processing with Google Earth Engine, and I do not think we will in any time soon, because the data they use are not the SLCs that we need. That have
They don't support any kind of complex data.
Right. I mean, it would be great if someone from Google would do that.
It's possible that they'll be able to use what we're planning for ISAR, the geocoded SLCs.
Right. Which will have the phase preserved. And you just have to difference them. They're already registered. The question about can we use StripMap app to process our own data? Yes, you can. You just have to edit the StripMap app.xml file to point to the data sets that you want to use, and then you need to set up the data set description files for your data, the reference.xml and the secondary.xml file. The format of that data description depends on what satellite it coming from. So different satellites have different file name and conventions. MVSAT and ERS, you have to have separate orbit files. That's just because other data sets, ALOS, TerraSAR-X, Cosmos SkyMed, they all include the orbit data with the data files, so you don't have to have separate orbit files. But for whatever reason, ESA has long decided to keep the orbits separate from the data. I guess because they want to update the orbits. Mm-hmm. But it makes it more painful to get the right data for processing. There's a philosophical question about XML in the chat. Any good reason to use an XML file to control input parameters rather than other formats? Well, it's very flexible. You can add more tags as you need them. I don't know if any of the ICE developers want to chime in with other reasons.
Because
I don't know.
Good reasons. There are reasons. I don't know if they're any better than any other.
It's easier to read than a JSON file, I imagine. Human readable.
Yeah, there's a lot of tools available for parsing them, and and navigating them, they can be hierarchical. There's all kinds of reasons for it. There's probably good reasons to not do it that way as well, but whatever reason, that's the choice.
Does anyone have an example notebooks for processing Cosmos SkyMed?
I don't think we have a Cosmos SkyMed notebook.
Not a
I
notebook, but
made
maybe
a notebook
an
for-
example XML file or two. It's really all
There's
you
the
need.
example XML files are there in the ISCE code. I sent a link to the Slack channel yesterday, the 2022 general channel. There's a link to where all the ICE input files are. So that's a place with there in the ICE GitHub. They're under examples input files. There's all input file examples for all the different satellites that ICE supports. You shouldn't have to make any other modifications to StripMap app. The whole point of having these sensor models is that in the very first pre-processing steps of StripMap app, it takes the data out of whatever format the data provider uses and puts it into a standard format for ICE that that StripMap app can do the rest of the processing on. So that's one of that's the concept for StripMap app, is that once you do this pre-processing step, then the rest of the processing is the same for all the StripMap satellites.
There's a question: can we do coarse and fine co-registration after geocoded terrain-corrected SLC data? I guess that means you're the not the interferometric SLC data, but the geocode. Yeah, you can't use that right now, or at least not the versions that Sentinel puts out. There will be a product for ISCE that is terrain corrected and geocoded that will be usable.
Right.
But Sentinel geocoded SLCs do not work for interferometry. Someone asked about where we'll be able to ask questions after the course, and the answer is that the Slack for the course will be permanent. We will keep it live, and in future, what we would strive to do is in future years use the same Slack channel for future versions of the course, so that there will be channels for each specific year, but also you have access to channels that will be accessible to everybody who's taken the course in the past, and that would be a good place to ask questions. There used to be a forum that had questions and answers in it. Is there any update, Paul, on what's happening to that?
The forum has been was taken offline because it was using old software that's no longer usable. But we have active discussion channel in the GitHub site. Just go to GitHub ICE and click on the discussion tab for in the GitHub.
That's
The disadvantage of that is that you have to get a GitHub account, but that's with the old forums system, you still had to get an account. The problem was that the old system, the way of generating accounts was not secure, and we had trouble with all kinds of hackers just creating spam accounts, and it wasn't possible to secure it.
My understanding is that Paul has a full copy of that old forum, though.
Well, I kind of lost track of that. I don't know if the Caltech person, he said he was going to hold on to it for a while, but it was a while ago when I asked him. So I don't know if he still has it. I should probably double check on it. I suspect it's still there, archived someplace.
It was really useful if that information could be put somewhere.
Yeah. I think it was in a form that if somebody would have to go in and convert it somehow for it to be actually usable. I will double check on that.
Maybe it'd be converted to XML. Someone's asking about full polarization InSAR data. Is there any impact of polarization over SLC data for InSAR processing? If yes, which polarization should be chosen? I guess the ALOS data is often available in dual polarization. Anyone want to step up and answer that? There are some differences, right?
The processing software works on one polarization in ICE, so you have to pick which one you want. Typically, you want HH or VV for most of the work because the signal to noise ratio is the highest. You get the highest signal, lowest noise. But there may be applications where you're interested in studying volume effects, like in forests or over agricultural areas, and then the cross-pol data may actually show you something quite interesting. So the short answer is use whatever the like pole is, HH or VV, as a default. And then once you become expert at it and you have puzzles that you can't answer because of phenomenology that doesn't make sense to you, you might look at the cross-pol data, HV or VH.
And ISAR is going to acquire a lot of dual polarization data. So we'll also have that same choice between the co-pol channel and the cross-pol channel for most places.
Right.
More questions. Updates on a netrc file functionality. Anybody still having problems? Well, we have 4 minutes before we're supposed to take a break. Four more minutes of questions. Okay. Does the phase from compact pole data, is it useful for InSAR or de-InSAR studies?
So if you have consistent compact pole observations as a time series, then you can certainly look at them interferometrically. It is a different phase mechanism, but in a differential sense. I suspect, just as with most things that are peculiar to a given pixel, they cancel to first order in interferometry, and you're left with just the geometric aspects of the phase observation. I think that would also obtain well for compact poles. So I think from that perspective, if all the data are in RH, RV, or are in LH, LV, you can do the interferometry, and probably to first order, it will look almost the same as if you had HH or VV data.
Three more minutes for questions. Everyone was great with the homeworks, yeah. Seems that way. No one's asking.
Either that or they didn't get far enough along to have any questions. It's a lot to learn.
Well, if there are no more questions, we should adjourn until 11. Let everyone stretch their legs, get a drink, eat their lunch, eat their dinner, delete as appropriate for time, for your proper time zone. I need to restart my computer, so I'm going to drop off and reappear because my sound isn't working properly. And my fellow instructors, I've made a request in the Slack channel about editing the notebook for the next exercise because the link is wrong for the homework folder. And maybe we'll all come back at 10 a.m. bright and fresh and ready for interferogram interpretation. I'll see you in 10.
11 a.m.
Yeah. Hello, everybody. I am just failing to use the GitHub repository in the proper way. Someone else has to do it because I have to do some presenting now. So the next thing on the agenda is our attempt to interpret interferograms, maybe in some cases for the first time. And I will share my screen and show you what I'd like you to look at in a second. All right. So, how's this looking? Can everyone see my screen? Let me turn my chat on so I can actually see what people say. Is there anyone? Okay, Boris can see it. Okay, so this is an exercise in interferogram interpretation. And I'm going to show you an interferogram. You're going to have some opportunities to play around with this. An interferogram was an earthquake that happened in Turkey quite some time ago now. This is an earthquake from 1995. It was a magnitude 6.4 earthquake. It struck the town of Dinar in Western Turkey. It killed about 90 people. And the earthquake itself had a surface rupture. So we know where the earthquake was because the fault actually broke all the way to the surface. And you could actually measure a small offset on the fault at the surface of about 30 centimeters. And I've included in this notebook the interpreting InSAR notebook in module 2.1. Here is the interferogram. Maybe I just zoom out a little so you can see it all at once. There you go. Maybe that's good. So here's an interferogram, and you can see I've got a color scale on here. It's a wrapped interferogram, which means that we have not converted these fringes into a continuous signal. The earthquake occurred in the period when the main satellites acquiring SAR data were the ERS satellites. So this is like the first generation of European Space Agency satellites doing SAR routinely. And you can see there are a number of fringes on this interferogram. What the exercise involves is trying to actually unwrap this interferogram yourself by hand using a profile. So looking at the data and trying to interpret what these fringes are showing you. Of course, important information that we have include the color scheme, the color bar, which shows that each fringe interval is 28 millimeters or 2.8 centimeters of deformation. In meters, of course, 0.028. And there's important information also in the figure caption. Specifically here, each cycle of colors from blue to yellow to red indicates an increase in distance between the satellite and the ground. Or in other words, a positive range change of 2.8 centimeters. So we go from blue to yellow to red. Okay, here's blue, yellow, red. That's an increase in range from here to here of 2.8 centimeters. Along with this interferogram figure, there's actually files that are uploaded here that you can open yourself if you wanted. For example, this is a PDF that you can print out. This exercise works very well on paper if you wanted to print it out. There's also, that goes with it, a grid shown here, which I would like you to draw your profile on. If you can print it out, then you can actually use these two figures together. The length of this grid here is the same as the length of this line here, if you print these two things out at the same scale. However, I anticipate that very few people who are doing this exercise have access to a color printer right now. So instead, I have a workaround, which I'll show you. Basically, you can click on a link here. A Google Draw document will open, and it includes basically the same thing, the grid and the interferogram, in such a way that you can actually manipulate it, and you can make a copy of this this Google Draw thing yourself, and use that to edit and do the exercise. You do not have permission to actually edit the original figure, so you have to make a copy of it in order to do this. And then you can take this line and put it on the figure and add dots in the appropriate places. And you can copy and paste the dots as well. So that's the basic idea of what I'd like you to do, but perhaps we can start with a mini primer on interpretation. So here is another interferogram. Hopefully you can see it. In this case, it's an interferogram from the Wells, Nevada earthquake in 2008. And here, each cycle of blue to yellow to red is again a movement of 28 millimeters of displacement in range increase. So blue, yellow, red, blue, yellow, red, blue, yellow, red, and so on. So if you were to pick a 0 level, perhaps we would use the first fringe that we can see here as 0, and then counting from looking at the colors and the color increment from blue to yellow to red, this would be another fringe interval. So this would represent 28 millimeters of displacement away from the satellite. The next fringe would be 2 times 28, so 56 millimeters. The third one would be 84 millimeters, and the fourth fringe would be 112. So in total, the interferogram, this signal in the interferogram of this earthquake is 112 millimeters of range increase. So that is consistent with the ground flexing down in the earthquake.
Just stop the video first.
Look, it's beautiful. It's a sea
Could
of
you please mute yourself, whoever that is? Thanks. So you're forming a little depression on the Earth's surface, 11 centimeters deep-ish. I mean, we have to account for line of sight, but in this case, we're just assuming that this deformation is vertical, in which case you have a little depression that's about 11 centimeters deep in the middle, over a distance of about 10 to 12 kilometers. It's a very, very subtle feature that you would probably not be able to identify yourself if you were there. So I would like you to do something similar with this slightly more complicated interferogram that we have for you. Try and figure out what the fringes represent and which way the ground is moving in each case, using the color bar, the color scale, and also the caption information that tells you which way the ground is moving. There's a couple more things to bear in mind when you're looking at this. One is that we've given you what we say is the 0 level. So we can treat this dashed line here as the line of 0 displacement. And we've even highlighted the first fringe here, and we say, okay, that's half a fringe of deformation between here and here. And also that this line here is half a fringe as well, but in the other direction. In terms of how you go about making this profile, my suggestion would be that you count from the outside of the interferogram in. We will say that both ends of the profile are at 0, and count inwards each fringe. And then on your map here, take your line, okay, and put it somewhere like here where the fringe crosses the profile line, and highlight a dot and drop it on, ooh, come on, drop it on the on the line where you think the displacement should be. Recognize, of course, that the color scale tells you what the displacement of a whole fringe and half a fringe is. That's one thing that you can, one piece of information to use. I've also included some other hints here. Oops, excuse me. I'll highlight it, but that's not going to do it. So 2.8 centimeters per fringe. That means that 2.5 fringes is 7 centimeters, and 5 fringes is 14 centimeters. And when you get to when you start counting these fringes, you'll see they start getting really close together as you get into the weeds down here. And at that point, I think it's okay to count every 5th fringe rather than every single one, because otherwise it will take a very long time to count them all and put dots on your profile all the way along there. And like I said, the Google Draw document is the best way to do this. There are other ways, but then they're not as readily usable. If you can print it out, by all means do. That. And then there are questions to answer as well, about what side of the fault you're on and how many displacements you get, how much displacement you get and in which direction, up or down basically, and then a few more questions here. And for these you can just edit the markdown cell, put your answer in, and then rerun it, and your answer will be kind of encoded in text. I will note also, yes, we are doing this now. That's the question. We are doing this now, and you're going to have 25 minutes to do it. And then at 11:40, we'll come back together and we'll discuss the answers. The link here to the homework folder is wrong if you haven't updated your notebook lately. I only realized this morning that it's still got last year's homework folder in here. So rather than use this one, use the homework folder that you have been using already, and save your answers there. Any other questions about what we're doing? Show how to get to the Google Draw? Sure. All you have to do is click on this link and then go up here and make a copy of it. And that will be your copy of it then, that you can edit yourself. Can I go over the instructions once more? I would like you to fill in this grid, putting dots on the profile where you think the displacement at each point is. So over time, hopefully you'll have a filled in grid with points on it, which show the progression of displacement on the interferogram from here all the way up to here, and then from here all the way up to here. In other words, I would like you to interpret the interferogram in terms of how much displacement is occurring at each point along this profile line. Any more questions? As I say, I think this will take you somewhere between 10 and 20 minutes to do. What we're going to do is I'll leave it here for you. Well, I'll be here to answer questions. If you have any questions, feel free to unmute yourself and ask, or type it in the chat. But but I would like you to complete this exercise. Starting from the notebook and answering the questions in the notebook, but also making your own version of this profile and the displacements along that profile. I'm going to repeat how to get to the Google Doc. There is a link in the notebook. It is on this section here, unwrapping the interferogram along a profile. Number 3, there is a link to Google Draw. Click on that and it takes you here. And someone sent a request to edit the file, and no, do not edit, do not request access to edit the file. Make your own copy of it. Go up here, click make a copy, and then you don't need to ask my permission. How do I interpret this ambiguous area in the second fringe? That's a really good question. And this is some of the nature of unwrapping, I would say, that computers run up against, right? Sometimes there's decorrelation and you can't really see where the fringe would be. For you, I would say, let me move this down. Yeah, I can. I shouldn't do that. In my copy, maybe. You can move this out of the way. You can see that, you know, there's a fringe here somewhere, and then there's a fringe there, and there's a zone in between, and you basically have to eyeball it and figure out where you would, in your expert opinion, that fringe might be. You can see that the fringes at this end are wider than they are at this end, so you have to kind of maybe factor that in as well. But I would probably say around here somewhere. You can see my cursor. I think maybe there, maybe a bit further left, somewhere like that. Interpolation, yes, that's basically what it is. You're trying to interpolate the fringes onto the profile line. I'm going to say, okay, this one, maybe, well, I'll move my dot off the line. Start here at 0. Half a fringe is maybe there. So this would be 1.5 fringes. Put a dot somewhere on here.
There are some places that are very noisy. That's what we call low coherence, and there's basically you have to try to guess where the fringe would be in that noisy area. So that's the reason that phase unwrapping is a difficult problem. Is it? When there's noise, it's not obvious where the fringe should be, and the software has to guess, just like you're trying to do with your brain.
Yeah, in the olden days, before we had robust unwrapping, we would have to often digitize the fringes ourselves in GIS, trace out the fringes and try and interpret them ourselves. What is the next step after placing the points? After placing the points, you know, on both sides, filling out your entire profile grid, there are questions in the notebook that you can write answers to, including how many fringes there are, what the displacements are, and what direction they're in. That's the first set of questions here. And then there are questions after as well. for example, what's the total vertical motion, which we call the throw of the fault, and that's the uplift plus the subsidence. So you can answer that. The ratio of uplift to subsidence, and you can even convert that then to movement on a fault. That's the final question. Why the line of sight values are not having negative values? Well, did I say they weren't negative? I'm not sure. You have the we're converting from range change to uplift and subsidence. Did I mention that? So interpreting whether the ground moved up or down along this profile is what we're doing. You asking is the question that why are we only looking at displacements from 0 to 0.028? Well, that's because InSAR measurements are all relative. In that you don't know where 0 is. You have to assume a 0. And then the line of sight displacement is one color cycle will tell you is a positive range change of 2.8 centimeters, but you can have the color gradient being reversed. It could go from red to blue, in which case going from the fringe that starts at red to the next fringe that starts at red, you might see, for example, here, you start out here and you count inwards, and you're going red, yellow, blue, not blue, yellow, red. That should tell you that the displacement is actually in the reverse direction. So you can have negative displacements, but you have to interpret the color gradient in order to figure that out, that they are negative displacements. Could I explain how I placed the first point again? Here is our editable version. What I did was I looked at where the first fringe crosses the profile line, which is, you see, this is the first fringe here, that white dashed line, and it cuts across the profile line about here. And then that is the first half fringe of displacement. It's a range increase because we're going the direction blue, yellow, red, which is equivalent to the ground subsiding about 1.4 centimeters. So I eyeballed it at 1.4 centimeters and I put in a dot there. I am not able to see any changes after placing these points. Are you sure you're using your own version of this file? If you're not editing your own file, then you won't be able to change anything. So you make sure you have your own copy, and this says copy. I can even I have named it. If you're working on your own copy, then I don't know why it's not working. Try again, see. You can copy and paste. If you need more dots, you can get more dots. You can drag them across. Oh, you can also resize them, which I didn't want to do. Control Z will undo. So my second point is going to be somewhere over here. At 1.4 plus 2.8 centimeters, that should be 4.2. And each of these divider lines is 2 centimeters. About here. maybe a bit further down, somewhere around there. I don't know how to solve your problems with Google Draw. I don't think there's any way of locking the figure. You should be able to move the stuff around yourself. Could you explain again how to determine the values based on the interpretation of the color change? Sure. So looking here, right, the first piece of important information is in the figure caption. It tells you what the sign convention is for deformation. Each cycle of colors from blue to yellow to red indicates an increase in distance between the satellite and the ground. Okay, so that means its range increase. And each fringe is 2.8 centimeters of relative range increase. So that means every time you go from the one fringe to the next, so from say this point here to this point here, the ground has moved a further 2.8 centimeters away from the satellite. Similarly, if you're in a place where the gradient between fringes is the other way around, so from this fringe to this fringe, if you look, instead of going blue, yellow, red, we're going red, yellow, blue. That is the reverse direction to the other side here. And that means that the ground moved 2.8 centimeters towards the satellite. In that case. So that would be a range decrease. And that would be consistent with the ground uplifting. So yeah, you rely on whoever made the figure telling you what the color scheme is and the sign convention. Otherwise, you don't know. But in this case, it's documented. So one side, some of these fringes are showed as you move inwards that the ground is moving further and further away from the satellite, and some other fringes show that the ground is moving closer and closer to the satellite. The black line here is where the fault was. So this is an area where the ground actually was broken by the fault. This is a point where we know the ground moved. And if you want more advice from me, do not try and continue your profile across the fault. And we might get into why that is when we go over the answer. Awesome. So people are getting these to work. Yes, you can end at the fault, but you can, of course, approach the fault from either end. So your profile can still be complete. It's just that don't try and continue from either end as you get to the fault. Basically, stop your profile, go from X to the fault, and then go from X prime to the fault from the other end. And you should you should see why that is once you've successfully done it. When you've finished, give a thumbs up or a wave or something, because that would be helpful to know like how people are getting on. We have some prodigious unwrappers amongst our group. That's great. I can't actually see everybody. I have to figure out how to make my talk window bigger. I see a few thumbs up though, that's great. The fringes always go from red to yellow, blue to yellow to red, except when they don't. If you count from outside inwards, like up in the north here, you see red, yellow, blue. And you see that. And then red, yellow, and blue again. So relatively speaking, moving from here to here, you are moving increasingly towards the satellite. So red, yellow, blue is in the opposite direction to blue, yellow, red. Another way of thinking about it is that if you stand here on the line, on the fringe, and you go blue, yellow, red, you're moving away from the satellite when you do that. So this is closer to the satellite than this. From X point towards the second, third, and fourth fringe, is there any noise, or is the fringe broken at the profile? I see a fringe right here. Maybe you could eyeball it again. You kind of have to interpret where you think it would be. You can see the blue here. You can see the blue here and there and there and there and there and there. So I think you just have to make your best interpretation of where you think it is. Is it a kind of deformation or landslide? This decorrelated area, I think, is a lake. Or maybe a field. I can't actually remember. I do have some figures later on that will help us to do this. How do the unwrapping algorithms deal with that kind of noise? That's a good question. So there's an algorithm called the branch cut algorithm that basically integrates around closed loops and figures out if you get back to where you started by looking at just 4 pixels, then the pixels are coherent. So it tries to do that. And in places where you have this kind of noise, that doesn't happen. So it doesn't try to unwrap through here is what it would do. Of course, Snafu tries to unwrap everything, which is one of the unwrappers that's built into ISCE. And what you should do once you have unwrapped using Snafu is take your correlation image and mask out things of low correlation, because you should not trust anything that unwraps in here. Often it will make up very large numbers of very large displacements when it's trying to unwrap something that's noisy. So you should just mask it out. Blue to yellow to red is away from the satellite. Yeah, that is correct. That's what it says in the caption. Blue to yellow to red is an increase in distance between the satellite and the ground. So the ground is moving away from the satellite. Is there a way to know where the satellite is located? Do I say in there? I don't think I do.
Yeah, this figure doesn't have a satellite look direction vector on it.
It doesn't. It's a descending interferogram. But we're treating all the motion as if it's vertical, so we are not trying to interpret it in terms of horizontal direction. What is the location? The location is Dinar, Turkey. It's given here. If you have Google Earth open, just search for the city of Dinar in Turkey, and you should find something. How to identify horizontal displacement? Well, you don't, because we're going to say there isn't any. You can only really do that if you have 2 interferograms, one from an ascending track and one from a descending track. And then you can tell from the sensors of motion in both interferograms whether patterns reverse or not will tell you something about the sense of motion. And tomorrow we have some notebooks where we can actually run models and see how the same earthquake looks different between an ascending and a descending track, and that will give you some intuition as to what you can look for in those cases. All right, we've got about 5 minutes. Can we give approximate values for the displacement? I don't trust my eyes. Well, yes, and as I think I said at some point, and it says somewhere in the notebook, once you get to the really dense fringes, you should just try counting in fives, not in individuals, because it gets very fiddly. And 5 fringes is 14 centimeters, which is a nice round number and easy to plot on the profile. Has anyone who has finished all the profiles tried to answer the questions? Yeah, thumbs up, thumbs down. Do we see? I can't see any thumbs up, but I'll split them. Oh yeah, 1 or 2. I have to click through all these names to see anything, unfortunately. So the questions are things like, how many fringes are there on the hanging wall? And the hanging wall, just for your name, is the name we give to the part of the side of the fault that is above the fault, which I have told you is the southwest side. So how many fringes in this area are there in total, counting from here to somewhere over here? Yes, that's a question. And then how much displacement does that represent? And is the direction of that displacement up or down when you're considering the movement of the ground? The ground moving up or down. And then the same for the other side of the fault, which we call the footwall. Did this side, how many fringes are there and which direction are they moving? And since we're at 11:40 nearly, maybe if someone is feeling brave, could they tell me how many fringes they think there are on this side of the fault? 22, says somebody. Okay. 23.5. 25.5. Wow. I guess you're counting in fives. They're all in the ballpark, what I think. Yeah. How much displacement does that represent? Anyone want to? About 6.6 meters, about 70 centimeters, somewhere in that range, yeah. And in which direction? Is the ground moving up or down? There's a strong sense of down, away from the satellite, which is down. Okay, great. And then on the other side of the fault, the footwall side, we call it, up here, how many fringes and in what how much displacement and in what direction? Maybe give all 3 answers in one comment. 2.5 fringes, 7 centimeters up. 2 and 5, 9.6 up. Great. Okay, fantastic. So we can go to my slides again. Okay, so let's do this. Just some terminology, footwall and hanging wall. The way to remember is that it's a mining terminology that the miners stood on the fault, so that was the footwall. That's the part of the fault beneath the fault, and the hanging wall is where you hang your lantern, so that's above the fault. But if you were to unwrap this interferogram by hand, this is how I did it. So, okay, 0, half a fringe, 1.5 fringes, 2.5 fringes. Then I started going in 5 because I got lazy. And your profile should look something like that. And then, of course, you hit the fault. So don't carry on. And then on the other side, start again at 0. Half a fringe is about here. 1.5 fringes is there, and maybe 2.5 is right by the fault. So in total, your profile should look something like this. It should have a very steep subsidence on one side of the fault and a very gentle uplift on the other. I said you could look this place up in Google Earth. This is what it looks like, and you can put your interferogram there. And you can see the reason for some of the decorrelation. Of course, these lakes are ephemeral, but there's a big body of water at the foot of the mountain, and there's big decorrelation in this area that's due to that. There's also, you can see some agriculture in the area, some fields that may have been plowed, some stuff. Some of the stuff that decorrelates is probably that, and some of the other stuff that decorrelates is probably due to other types of vegetation. You can also see this lake is decorrelated. There's some decorrelation at the foot of the slope. That's probably slope decorrelation, all that good stuff. And I don't remember if I included these files to download, but you can get them because this is part of a teaching exercise that I use in some of my undergraduate classes. And it's actually part of a UNAVCO developed curriculum that you can download from their website. Okay, so what did I get? I get 21 fringes of subsidence and 2.5 fringes of uplift, but you can say there's probably some slop in terms of the number of fringes. So in total, I get 59 centimeters of subsidence and 7 centimeters of uplift and 66 centimeters of total vertical motion from one side of the fault to the other. If you read back through the notebook, you'll see that I reported that the surface offset of the fault, so the movement of the fault was 30 centimeters at its largest, and this indicates that there was more movement of the fault below the surface than there was that made it to the surface. So the amount of fault slip, we would call it, the actual movement of the fault is larger at depth than it is at the surface. And you can convert that to a amount of slip on a fault just using trigonometry. It's pretty simple. You can draw a right angle triangle. In the notebook, I mentioned that people think from seismology that this fault was dipping at an angle of 40 degrees. It had 66 centimeters of vertical motion. So just dividing 0.66 by the sine of 40 degrees, you get about 1 meter of movement on the fault. Which is about right for an earthquake in kind of the mid-magnitude 6s. When I teach this, there are other questions I ask. I ask students to compare the uplift profile to the topography and how many earthquakes might it take to build the topography that you see, and does it look like the topography? Well, it doesn't look like topography much. You can see the topographies here. There is uplift in the area that went up in the earthquake, and there's maybe subsidence in the area that went, or there's depressed topography in the area that went down in the earthquake. But one earthquake is not the whole story for the tectonics in this area. And they're not similar, but we might not expect them to be. We might expect the topography to look more like some kind of sawtooth shape. And that's because you have hundreds of years of bending of the crust between earthquakes before you have the earthquake itself. And if you treat the orange dash line as more of what you're expecting to see, then the topography looks a bit more like that. Of course, there are other geological processes that go on that mean that they don't look exactly the same. For example, you get erosion of the rocks that have uplifted, and you get deposition of sediments in the areas where the rocks are thrown down. So that partly explains why the deformation we see does not look like the topography exactly. But some of the things that you do see are consistent with where we see subsidence and where we see uplift. For example, if we go back to this figure, there are lakes up against the foot of the ridge. So this is clearly consistent with this being the part of the ground that goes down the most. And that's where water will drain to. And that's why there are all these lakes ponded up against the ridge there. So the question, when we do profiles, we should attempt to look at the line as perpendicular to the fault as possible. That would be good practice, yes, because then you should see the, then you have a representative pattern of what happened with distance. Some people do strike fault parallel as well as fault perpendicular profiles. That should show you the how the deformation dies away with distance from the maximum. That should tell you something about how long the fault might be if you do it that way. Is this the first homework for today? Yes, it is. I would like you to complete all the questions in the notebook and complete your profile and turn them both in as printouts, saved PDFs. Are there any other questions about this? We are almost at the end of our 50 minutes. Are there situations where making profiles by hand is more beneficial than using an algorithm? I would say so, yeah. And that is when you don't trust the results of your unwrapping. Sometimes you can look at your unwrapped interferogram and you'll see that there are blocks of unwrapped phase that are discontinuous with the phase around them, or that possibly are discontinuous. And it's sometimes beneficial to go and actually manually look at the interferogram and make sure that your unwrapping result is valid. Sometimes you'll see that it doesn't look that way, and then you might have an issue. You might have to actually fix your interferogram somehow. For example, manually in GIS, changing the value of a whole area by multiples of 2 pi in phase to make them match. What is the range of acceptable error on this type of observation? I'm going to say in this case, probably to the nearest half fringe. I mean, you might have an integer ambiguity of fringes of about 1 because it's difficult to count them when you get down into the weeds here. So somewhere between half and 1 fringe. Is it possible to map unknown faults using InSAR? Earthquakes happen on unknown faults all of the time. And so yes, we have successfully mapped unknown faults using InSAR. Eric and I worked on an earthquake in Iran nearly 20 years ago, in which there was one map fault in the area, but the earthquake did not occur on it. When we looked at the interferogram, we saw that the fault was offset by several kilometers from the map fault in the area. And we sent the field team from the Geological Survey of Iran back to the area and telling them that we thought they went to the wrong place. And when they went there, they found the fault that was the source of the earthquake. So absolutely, yes, we can map faults that we didn't know before.
That was the 2003 BAM earthquake, and that killed a lot of people in southeast Iran.
Yeah, because the fault, it turned out, ran right into the middle of the city. For creeping faults, the fringes might be way more spaced, right? Maybe because the amplitudes of motion would be small, but you would see a very sharp transition. Like all of the slip should be occurring near the fault, so you would see a large offset right at the fault. In that case, the maximum displacement should be right next to the fault if the fault is moving at the surface. What focal depth and magnitude of earthquake can be sensed by InSAR? We have we routinely see earthquakes of magnitude 6 and larger easily in the top 20 kilometers of the crust. If you go to smaller earthquakes, typically they need to be shallower to be detectable. The smallest earthquake that's ever been detected, I think, is a magnitude 3.5. It was in the top few hundred meters of the subsurface. It was in a quarry, and I think now in good atmospheric conditions, you can detect shallow earthquakes down to magnitude 4.5. Not consistently, but it has been done. Basically, it depends on the depth. There was a trade-off between depth and size for detectable earthquakes, and the deeper the earthquake is, the bigger it has to be for you to be able to detect it. For the dike intrusion interferogram from yesterday, we saw opposite patterns, fringes across from each other. I guess on either side of the dike. So on one side of the dike we have uplift, and the other we have subsidence. Is that correct? It's probably not correct. A dike would be a horizontal opening, and so some of the difference you're seeing there is probably that horizontal motion. Like in that case, you might get a combination of vertical and horizontal motion. You usually get some uplift and an opening at the same time, and the interplay between the uplift and the opening might cancel on one side of the fault and might sum on the other. So you might see one side of the fault, the dike, you get almost no deformation because the horizontal and vertical motions are canceling, and on the other you see a bigger signal because they're adding up. I think that's what happened for that particular dike intrusion.
See Gareth's paper on the BAM earthquake for an explanation of how the vertical and horizontal adds together on different sides of the fault.
That's true, and we reproduced that in a notebook tomorrow, so we can look at that too. Like, yeah, we often see it for strike slip faults as well, where you have the same kind of thing. Like all of the signal appears on one side of the interferogram, and when we first saw it, that was very confusing. But then we made some models and then realized that it was actually what you should expect to see. Is the spiral-like pattern of the topographic change gradient around the fault typical? It's not spiral. That's an important point. It's concentric. These fringes they're not exactly parallel to each other, but they're completely contained within the inner fringes are contained within the outer fringes. And that's something that is typical. What is the use of measuring deformation rates after the earthquake? Well, of course, we do want to understand what happened in the earthquake. I had a similar kind of philosophical, not crisis exactly, but I did wonder whether or not that my efforts could be put to other use. So I started studying the bending of the crust between earthquakes, which allows you to measure the loading rates on faults, and maybe is more useful as information for society. But understanding earthquakes is still an important part of our research, to try and understand how they happen. And I certainly, having made my career studying earthquakes, I don't think it's a completely pointless use of your time. Let me see. If a fault had horizontal motions, would we see a bit different pattern? We will look at a horizontal moving earthquake tomorrow. Yeah, you see a different pattern. And also how it resolves into both ascending and descending interferograms is different. So this particular case, if we had an ascending interferogram of it, it would look similar to this. It would have subsidence in the same area and uplift in the same area, because of the way that satellite line of sight works. All InSAR interferograms are sensitive to vertical motion, but they're differently sensitive to horizontal motion. And so looking at two interferograms can sometimes help you tell whether or not it's a horizontal or a vertical motion that you're seeing. Would it be possible for InSAR to detect sinkholes? Yes. Yes, you see decorrelation in the area where the sinkhole happens, and I think there have been cases where people have identified precursory substance before the thing completely collapses.
Yeah, we saw that with UAV SAR data in Louisiana.
That's right, and yeah, I've seen it in other places too. Places where they, like in New Mexico, I think, where there's brine mining. They suck a lot of, they use water as a means of like extracting salt. The surface then subsides as materials removed underground. We could observe fringe patterns after a seismic swarm. Would it have the same pattern like an earthquake? Certainly people have seen something like that, so a pattern that's consistent with fault slip. That's happened in Southern California near the Salton Sea, where there are lots of earthquake swarms. There are 7 more questions. I'm well behind here. Is that all of them? Yeah, so often what's seen with earthquake swarms is that the earthquakes are, when you add up their seismic moment, which is the equivalent of energy, it's not exactly the same thing. The slip is often, the fault movement is actually much larger in amplitude than the earthquakes added up. So often these are driven by fault movement, and then the seismic swarm is like a symptom. It's like from the stresses that are imparted by the fault moving, that actually triggers all these earthquakes. That was a great set of questions. We have come to the end of this exercise. I propose maybe another 10-minute break. Maybe we should start the next session at 10 after the hour. So that would be 12:10 Pacific time. I assume Eric's probably okay with that.
Sure, 12:10 is good.
Yeah, Eric's up next, and we will talk about processing Sentinel interferograms using TOPS app, which will be fun and hopefully very useful. I will see you all then. I'm going to eat my sandwich.
I'm gonna eat some yogurt.
Well, you've had none. I didn't unpack yet. I didn't unpack. You heard? You
Okay. Hopefully everybody had a nice break. Eric, are you there? Well, I'll just wait for Eric to situate himself. The next exercise is TOPS app processing. Which is the package within ISCE that deals with processing Sentinel interferograms. Excuse me.
Okay, sorry, I'm trying to use two screens here to be able to see the chat while I'm sharing things, and it makes Zoom act a little bit differently. Zoom somehow knows that I have a second screen, so it's smart about that. Yes, so we're going to be talking this afternoon. This is actually quite a long process to process Sentinel-1 data. It's quite a complicated. It's much more complicated than the strip map processing that we did yesterday, because of the way the data is acquired. So we're going to have to do a significant amount more work to get a good quality interferogram. We started with the strip map app because it's easier to understand what's going on. And now we're going to be talking about the TOPS mode, which is a special type of scanning radar that's used by the Sentinel-1 satellites. It's Sentinel-1A, Sentinel-1B, and soon to be launched Sentinel-1C. It's also used sometimes by the SAOCOM satellite. It's launched by Argentina, but I believe that the SAOCOM satellite, when it acquires data in TOPS mode, it's not acquired. It was not designed to be used for interferometry. They made a very careful design of the Sentinel-1 satellite to make this TOPS mode operate in a way that interferometry is possible. That requires that they have the satellite position and where it starts sending out pulses very accurately located in space relative to the Earth. So that requires a very it needs to be designed in advance, and that's what Sentinel-1 was designed for. So we're going to talk about that today. So we have a notebook here, TOPS app. It's mostly, but it's called, the processing program is called TOPS app, topsapp.py. And the notebook here, of course, has the usual preliminary setup parts, importing a bunch of stuff. So first, we want to take a little bit of time to explain what the TOPS mode is. It's a way of collecting data over a wide swath by collecting data in 3 different subswaths. There's reasons that it's more difficult to just collect data over a wide swath. There is a special technique that's going to be used on the ISCE mission called SweepSAR, where we get a wide swath without doing this subswath system. But the ISCE mission will be the first satellite to do that SweepSAR method. There's no existing satellites that use SweepSAR. The existing satellites either use this TOPS mode to get subswaths, or the ALOS 2 satellite uses ScanSAR, which is quite similar in doing subswaths. So the subswaths are created by the satellite going along the track and sending out a number of bursts along pointed at one subswath. And then they change the antenna and send out a number of bursts, a burst of pulses in another subswath. And then they switch again to the third subswath, another burst of pulses, and then they switch back to the first one. So each one of these subswaths is collected with a number of pulses that are contained within a burst. And the special thing about the TOPS mode is that they actually also scan the radar antenna in the along track direction during the burst. And that's why you can see in this this drawing here, there's a divergence of the radar look direction within the burst. And that is a special feature of the TOPS mode that is designed to give better quality to the amplitude images for people that are studying forests or agriculture with the amplitude images. But it actually makes our life much more difficult for interferometry, because the radar line of sight is actually changing within each burst, and that causes extra complications that the processing software has to deal with. So as we once we start looking at the images, we start the ISCE software deals only with the SLCs from Sentinel-1. Some people actually process the Sentinel-1 data from the raw data. ISCE does not do the focusing for Sentinel-1 raw data. It only works with the Sentinel-1 TOPS mode data that's in SLC format, already focused. And the European Space Agency does the processing for the Copernicus missions. And so they give us files where there's a separate file for each one of the 3 subswaths. And then there's also separate files for each one of these bursts. So you can kind of think of these bursts as little separate SAR images that are each processed. We actually have to work with them separately for a large part of the processing, and then at the end combine them into a larger image. And that's a unique feature to the TOPS mode. It's largely similar for ScanSAR data from ALOS 2, but the ALOS 2 ScanSAR doesn't have this along track scanning aspect that gives additional complications that we have to deal with. And these bursts are about 70-80 kilometers across track in each subswath, and 20 kilometers along track. So that's a relatively small area for
right. So now
so the if you want to cover a big area, you're going to need to use a lot of bursts. And the full track width is 250 kilometers. They cut the data up into frames, into what they call slices. They're not frames in the like other satellites. Other satellites have a set of well-defined frames that have a certain latitude and longitude extent and always keep that extent. For whatever reason, the ISCE has decided to just they process the Sentinel-1 data in long strips, and then they cut it up into slices. And the slices can be a different slice of that long track, depending on how they did the processing. So usually there's 9 bursts in each one of the 3 subswaths, or a total of 27 bursts in one slice. But sometimes the slices are slightly different sizes. If it's at the very end of a data take, and the hassle that happens with Copernicus Sentinel-1 data is that these slices are not always lined up. The bursts themselves are lined up, so once we get the bursts pulled out of the slices, then we can do the InSAR processing. But to get the right bursts, you might need to get a different slice sometimes, and that's one of the hassles with Sentinel-1. And that's why we were talking earlier today in the homework discussion session about the new plans to have at ASF a way to download the bursts separately, as opposed to these slices that the European Space Agency creates for organizing the data. And one slice is about 4 gigabytes when it has dual polarizations. Okay, most of the time over land they use VV and VH. Over Antarctica and Greenland, they use HH and HV polarizations. And in a few places, they've acquired data with only a single polarization, which is generally a VV. So that's kind of a basic introduction to this TOPS mode. It's kind of a big complication. What's going on here? Why is my notebook stopped? Let me restart kernel. Okay. My notebook says it's downloading something. Let me see if I try a different copy of this notebook, and it might run better. Oh, darn, it's stuck. Hold on a second. Let me shut down this server and restart it. Sorry about that. It was working earlier. So the TOPS mode is has these complications of the bursts. Basically, what we need to do is collect the bursts out of the slice files that we get from ISCE or ASF, and then we need to. It pulls out all the bursts. It finds the bursts that are the same between the two dates, and puts those into actually the ICE software is very smart. It doesn't unlike with the strip map app, the TOPS app doesn't actually make copies of all those original burst files. It actually just sets up virtual virtual data sets that point to the original burst file. So in fact, if you look at let me try this other one. The burst files, they're actually just links with virtual data sets. Okay, now it's working. Sorry about that. So you can use the Sysera federated query to download data from the ASF. The Sysera query is written here. We also have this code here to do the usual download from the ASF data pool. It's very similar to the download of the ALOS data that we did yesterday. You have to have your netrc file with your Earth data login, and all that part is exactly the same. In this case, I've already downloaded these files, so we're just gonna go ahead and look at them. So each one of these slices comes in a zip file, and that zip file has a lot of files internally, but ICE knows how to actually access all of those files that are inside the zip file without having to unzip them. And so that actually is another way that we save space, by just reading the data from these zip files without having to unzip them, because they actually would get bigger than 4 gigabytes each if you unzip them. So I'm going to skip the step about doing the download from the stage data. Again, we have the so the next thing we have to do with Sentinel-1 is download the orbits. There's this download app in Sentinel in the ICE app, in the ICE directory, called deload orbits. Okay, this is going to be doing the way this particular notebook is set up. It does the processing in the same directory where the notebook is loaded. And you need to have this deload orbits.py Python code in the same directory where you're running the script. So when we run this, it goes out, and I'm telling it to download the orbits between 2020-05-11 and 2020-05-18, and that brackets the time interval of this data. Oh, I should also mention that the Sentinel-1 data files have the date in them, unlike the ALOS data files. This part of the file name is the date it was acquired, and after the T here is the time of day in hours, minutes, and seconds, and so that tells you exactly when this data was acquired. And this other part of the file name is the orbit number. So we've already got the orbits. We're going to go back to the home directory of this processing. If we look at the orbit directory, it's downloaded all the orbits in those 8 days. There's an extra cell here in case the orbit download didn't work. So now we're finally now we have the data files, for the 2 dates and the orbits for the 2 dates, and we're ready to run TOPS app. You can run TOPS app help help and see all the options in TOPS app. We're not going to cover all those options. This is the basic TOPS app XML file that explains what we want to process. And this, you can specify, you just like with the strip map app, we specify the input reference scene with a reference XML file and a secondary scene with the secondary XML file. You can change the number of looks. You can change the region of interest. You can specify which subswaths. There's the 3 subswaths. In this case, we're going to specify that we want to do the phase unwrapping, and we're going to use the snafu unwrapper this time and not the ICU unwrapper. And we're also going to do what they call dense offsets. That's the pixel offset tracking or dense offset at the end of the after the interferogram. So we're ready to go on. These are the reference XML file has to have a list where the orbits are here. And so when we, just like with StripMap app, we specify the output directory, just calling it reference. And the format of these ISA zip files is called safe format. I don't remember what that stands for, but it's got some acronym. And so you just give the zip file name and it automatically knows how to grab the files it needs out of that zip file without unzipping it. Or it unzips it within the program. So we just wrote those files as specified earlier. I've already run the processing here, so we can see that I have, so the processing is done in this directory called InSAR. We can take a quick look at the tops app dot, oops, not tops, that's the wrong one. It's tops app.xml. And it's just as I explained, we're going to use the reference XML, secondary XML. We're only going to process subswath 3 because we know that this particular earthquake is only in subswath 3. And we have this region of interest specified. And just like with the StripMap app, there's the steps option, which is a good idea to always do that, because then you can, it saves the results after each step. And this just explains what all the steps are in the TOPS app processing. They're some of them are the same as what with StripMap app, but there's some of them that are different. This is just an extra check in case you didn't get your XML created. So now they run the first step, which is going through the 2 slices. In this case, we gave an area that we wanted to process, so it looked at the slice, and it saw that there were 9 bursts in that slice, and but we only need 4 of them to cover the area that we asked it to process. The second slice actually has 10 bursts. Oh, wait a minute. No, that's the it has to do this for each one of the 3 subswaths of the first scene. And then it does it for the 3 subswaths of the second scene. So now we have extracted the information for 4 bursts of each of the 2 scenes. And it's automatically determined which bursts are the same in the 2 scenes. And this information is saved in the pickle directory. That's where when we run steps, it saves the information about the what's been completed. Since I've already run all the steps, I have all the pickle files here. If I had only run just the startup step, then I would only see the startup pickle. So now it's created our for the reference scene. We've only asked it to do subswath 3, and if we look at the subswath 3 reference directory, then there's the 4 bursts here. And as I mentioned earlier, it doesn't actually copy the burst. data here. It's only created this VRT virtual data set that points to the burst within the zip file, but you can see that there's the 4 bursts of the SL of the reference scene, and it's also created this bottom and top overlap information. The bursts of a Sentinel-1 TOPS mode overlap a very small amount, but it's very important to know what that amount of overlap is, because that's the way that we do some of the later steps. So that's what this burst reference overlaps information is, and we get that information from the burst timing and the orbit data. So the next step is to verify the DEM. I've already run this step before, so it's not going to have to go out and download the DEM. If you haven't downloaded the DEM yet, it'll do that. In this case, it's determined that we need the DEM between 37 degrees north and 39 degrees north, 119 west longitude, and 117 west longitude. So I've already got that DEM ready. There's another cell here in case the DEM download didn't work. So now we're ready to do the topo step. This topo step is very, very similar to what we did with the strip map app. It's taking the information from the orbit data and the DEM and figuring out which points on the DEM surface go into which pixels of the radar image. So it's creating up this geom reference output. In this case, we're only asking for subswath 3, so it's only going to do the geometry calculations for subswath 3, and it's very similar process, although there's a little bit of extra complication because of the burst. So it actually has to set up a separate geometry file for each burst. It's as though each burst of the TOPS mode is a separate image, rather than that we have to treat separately. So it first did the geometry reference here for the first burst, the LOS1, the latitude, longitude, height, and line of sight vectors and radar coordinates for burst 1. Now it's working on burst 2, and it'll do. We have 4 bursts here. After that, when that's done, we'll be able to look at the reference. Okay, it's done with the second burst. This is one of the processes in ISCE where it uses all 16 threads that are available on these virtual machines. So it's running pretty fast. And you can see here that the full DEM was 7,000 by 7,000 pixels. It's only using 4,000 by 2,000 pixels. And it's the burst has 2,000 lines and 1476 pixels. So it's up to 1,000 lines. Okay, so now it's done with the 3 bursts. With the third burst, there's one more burst to do. There's a little question here that you can answer at your leisure is this line of sight RDR file has the line of sight vector, which is the incidence angle, which actually has two bands to it, the incidence angle and the along track direction component of the azimuth angle of the line of sight vector. And now it's done with all four bursts. We can, because these files are GDAL compatible, we can use GDAL info on one of these bursts, and the line of sight vector here shows that with the regular GDAL info statistics, the minimum angle of this line of sight is the incidence angle is in band 1, so it goes from 41 degrees incidence angle to 46 degrees, and the azimuth angle is in band 2. The azimuth angle is not changing very much, so we the numbers are very similar along track here within the burst. So now we can take a quick look at what the burst looked like. The height this is the elevation within that burst in radar coordinates. This second plot here is the incidence angle within the burst. The incidence angle, of course, increases as you go across away from the satellite. Remember that we always have the left side of the image in radar coordinates is the side that's closest to the satellite. So the incidence angle is closer to vertical here. We measure incidence angle from the vertical. So there's a small incidence angle near the satellite and a large incidence angle further away. And the azimuth angle is also varying along the burst, but I'm not gonna. This is due to that scanning action. With a ScanSAR satellite, there's not this long track scanning, which is it's an extra complication. So the next steps are actually going to be because of this along track scanning. We need to make sure that the two scenes are very precisely aligned to within 1,000th of a pixel. The TOPS app includes this method that's called enhanced spectral diversity, where we actually form interferograms in the overlap between the two bursts. There's only a little bit of overlap, but we're going to make an interferogram for that overlap between the two bursts. That's what it's doing now. It's setting up the overlaps and doing the geometry and the calculations for the overlaps. And it does that for both the reference satellite and the secondary satellite. And there's a whole explanation in Haresh's paper about what all this is doing. I'm not going to go into a lot of detail, but basically, by taking the interferogram in that overlap region for the reference scene and the interferogram of that overlap region in the secondary scene, and comparing those two overlap interferograms, then we can determine exactly what the along track shift is between the two scenes. That's what the rest of these steps is doing. It's still doing the calculation here. I'm waiting for it to finish run. So it actually it has to cut out a piece of each one of the bursts and to make a separate SLC and to form the interferogram with the top of one burst we're taking the top of the top of the bottom burst and the bottom of the top burst, which is the overlap between the scenes here. And it has to do that for each one of the burst overlaps. In this case, we have 4 bursts. So there's 3 overlaps, the burst 1 to burst 2, burst 2 to burst 3, and burst 3 to burst 4. It actually makes a separate little virtual files for each one of these overlaps. And this is why, in order to do this ESD step, you actually have to have at least 2 bursts. So that's one thing that TOPS app requires. If you're going to do this, this enhanced spectral diversity, is that you cannot process an area that's less than 1. You need to have at least 2 bursts in order to have this overlap between at least 2 bursts. So that means you have to have an area that's at least 40 kilometers along track rather than only doing 1 burst. So it's a so this is a complication that's specific to TOPS mode. Other satellites like ISCE, we won't have it. There's no bursts in ISCE. This is a complication that's very specific to TOPS mode, and the Copernicus people in ISCE designed the Sentinel-1 satellites to use this TOPS mode almost everywhere. So this is what we have to do. They actually were telling us about this, about 15 years ago, and we said that sounds horrible for InSAR, but we did once we got the data, we very smart radar engineers figured out how to do this processing of the overlaps. I couldn't tell you exactly how it works, but that's what Haresh and Piyush and the other radar engineers do. Okay, so now it's starting to plot the data. So first it's plotting the SLC from. So this is the bottom of burst 1. No, this is the bottom of burst 2 and the top of burst 1. The amplitude images should look the same here because it's the overlap between the bursts. And maybe you can see here, this is burst 1, and you can see that we're using just the bottom of burst 1 here. And the top of burst 2. And just like with the other interferograms, the phase of the SLCs is random until we form the interferograms. So the next step, first it does coarse offsets. This is very similar to like what we did in the, it's determined the offsets between the two the 2 bursts from the orbits. It's estimated what the offset is, then it resamples the this is just a plot of the offsets in azimuth and range. And just like what we did for strip map data, we use these offsets that it calculates to resample the data from one burst into the geometry of the first burst, and then finally do the overlap interferograms. So as I mentioned before, we have we have a total of 4 bursts. That means there's 3 overlaps between burst 1 and 2, 2 and 3, 3 and 4. And those the burst overlaps are just at the very top and bottom of the burst. So the overlaps are separated by almost 20 kilometers. There's only about 2 kilometers of overlap between bursts. And then there's 18 kilometers before there's the next overlap. So this first overlap interferogram is kind of a funny looking interferogram because it's highly discontinuous. These overlaps are actually, even though they're plotted together, they're actually 20 kilometers apart, which looks kind of strange, but that's just the way it is. That's another disadvantage of the way the TOPS mode works, that the overlap between the bursts is very small. It calculates the coherence for each one of those burst overlap interferograms. In this case, the coherence is very high because it's out in the Nevada desert. There's no trees or anything to mess up the coherence. And then it makes these combined interferograms, and the combined interferogram is the difference between the burst overlap interferograms from the first date and the burst overlap interferograms from the second date. And that's what we need to actually understand what's the long track shift between these two dates. That's an adjustment to what we get from the orbit data. And so this plot on the right shows this is the wrapped phase from the burst overlap differential interferogram. It's a differential interferogram because it's the difference between the first date overlap interferograms and the second date overlap interferograms. And now the program goes through and it estimates what's the amount of a long track shift in pixels that causes this phase of the differential interferogram. And you can see it's quite small, but it's a little bit, since we need to get within 1,000th of a pixel, the average here is a little bit larger than 1,000th of a pixel. So it also so we need to do this enhanced spectral diversity correction to make sure that that we've removed this additional shift. In most cases, this is actually this azimuth shift is due to the ionosphere. Even though C-band is less affected by the ionosphere, it can have an effect of 1,000th of a pixel in the long track direction. And we're not going to cover it in this talk, but we can also do another type of calculation to estimate the ionospheric effects from the Sentinel-1 and get this azimuth shift from the ionospheric estimate, and not do this empirical calculation with the ESD. That's sort of an advanced topic. So we also want to make sure that we have the range. So the ESD calculation only estimates the long track misregistration. We do the range direction misregistration with the same kind of amp core that we did with the strip map data on the amplitude images. And this then uses the burst overlap SLCs. And it's there's not very much data here, so it's very quick. And we can also estimate what's the misregistration in the range direction. It'll be done in a minute. And this is one of the things that it's a real hassle with Sentinel-1 data that we're not going to have with ISCE, because ISCE doesn't have this TOPS mode. We're just going to have the sweep star is very complicated in in the raw data, but once we form the SLCs from the raw data, then the raw data from NISAR is going to be essentially like strip map data. A lot of work is going to go into the focusing of the NISAR data, but once it's focused, it's going to be essentially very much like the strip map data. That's much simpler to deal with. There's none of this bursts and so that's what NISAR is going to have, this sweep SAR system that's going to be, it's a way of getting the wider swath without this complication of the strip map of the TOPS mode. So this is the range offset in pixels. You can see the range offset's a little bit bigger. This also could be due to the ionosphere. We're not doing the ionospheric estimates in this notebook, but so now that we've determined the optimum range offset and the azimuth offset, we use those to generate, to actually resample the images in the overlaps and then do it for the whole burst. No, it just resamples because now we're going directly to processing the whole burst because we've determined what the overlap is with these overlap interferograms, and now we're ready to take the whole secondary scene bursts and resample them into precise co-registration with the primary scene bursts. First, it generates the offset files. And then does the resampling. Are there any questions as we gotten to this point? See, people are asking about sweep SAR. Yes, NISAR will have sweep SAR mode. The big advantage of sweep SAR is that once it's processed to an SLC, it's essentially the same as a strip map, but it's actually 250 kilometers wide instead of 70 or 100 kilometers wide. I don't know. At some point, we're supposed to take a break for 10 minutes. Is this a?
This would be a great time.
I think this is a good time to take a break.
Because people are running topo and it's taking a long time, and maybe.
Okay, so it's 1 o'clock here in California. So let's come back at 1:10. In California time.
And I can stay on here troubleshooting people's NetRC things if for those who are still having issues in the chat or in Slack. Actually, I'm getting both. Yeah, see everyone else at 1:10. You want to put up a vacation message there, Eric?
Yes, I'm just changing the slide here.
Cool.
So I'm going to take a little break. Okay, so I'm back here and it's just about finished with my processing of the resampling steps. We can go back here to see what it's been doing while the last 10 minutes. The first thing it does is actually have to calculate the offsets. This is very much like what we do with the strip map data. Once you have all this orbit information and misregistration information, then we can calculate the offset of the secondary scene relative to the reference scene for every pixel in the secondary scene. So that it does that for each burst. So here's the range offsets for burst 1, azimuth offsets for burst 1. This is a lot of calculations. And it's doing it's finished with burst 1. It starts on burst 2. So it's actually, it has to do a lot of calculations. And then once it's finished with the range offsets and azimuth offsets for each burst, then it can use those offsets to resample the secondary bursts into the same exact co-registration with the reference bursts and get the co-registered SLCs. So you can see here, we did an LS on the fine offset. So it's done all these offset files. Those are the offsets for every pixel in the burst. And then we can go to the next step. So at this point, we could actually do the ionospheric estimation. We're not going to do that in this notebook. That's a whole nother topic. We're going to talk about that tomorrow with strip map data. It's similar, but even more complicated for TOPS mode. But now, once we've gotten all these co-registered SLCs, we can just make interferograms. And this is making interferograms for each burst of the area that we've selected. It's also taking looks. We specified at the beginning in the XML file here that we want 7 range looks and 3 azimuth looks. For strip map data, the azimuth spacing of the pulses is normally much less than the range of sampling. So we take, for strip map data, we normally take more azimuth looks than range looks, but in the TOPS mode, the way they process the SLCs, we need to take fewer azimuth looks. The pixel size is around 14 meters in the azimuth spacing of the SLCs, and the range spacing is 2.3 meters in slant range. So we're taking more range looks and fewer azimuth looks for the Sentinel-1 data. So it's just finishing. It made the interferogram. It's calculating the correlation image. And you can see that the for each burst, it has a larger number of pixels across than it has along track. That's because it's even now that we've taken looks, the pixels are closer to square, but the bursts are much wider across track. They're about 80 kilometers wide and only 20 kilometers long. So the number of pixels is more. And in fact, what we do here is calculate the correlation on the full resolution interferogram before taking bursts. So that's why these numbers are much larger. This is the size of the burst before taking any looks. And we calculate the, this is the full resolution correlation. So the processing actually forms the interferogram at the full resolution, and then it takes looks. So we get both a full resolution interferogram output and one with that has the 3 azimuth looks and the 7 range looks. For each, these are still being done for each burst separately. And then at the end, it runs this step called merge bursts. And this is, now that we've actually formed the interferograms, we're finally able to, and taken looks, we are finally able to merge these bursts together into a new merged interferogram. So the merged interferogram is called topophase.flat. And there's both a topophase.flat.full. That's actually a virtual interferogram at the full resolution. And then there's topophase.flat. That's the interferogram after merging with the looks taken. And this is the same name as the strip map app interferogram. But it's in this directory called merge because we've now merged the bursts. If we go back over here, there's a new directory in the in your directory here that's got the interferogram, the Sentinel-1 TOPS interferogram that after the merger of the bursts. There's also the fine interferogram subswath 3, and these are the interferograms for each one of the 4 bursts. But unless you have some reason to look at that, you don't need to look at it. Mostly what you're going to work with is this merged interferogram. It also does the standard power spectrum filter and power spectrum phase effective correlation to make the phase sigma correlation. So now, as I was just saying, there's the interferograms for the separate bursts, and we can look at the interferogram for a single burst. This is the burst that happens to be this is burst number 3. This is the burst that contains most of the signal from this earthquake in Nevada. So it has a big part of the signal, but it's not the whole thing. So we want to look at the merged interferogram. And that has all 4 bursts. And now we can see the full earthquake pattern with the 4 bursts and this single subswath. This is a magnitude 6.1. I forget exactly. And it's a strike, a largely strike slip earthquake. So we were talking earlier in Gareth's explanation about earthquake interpretation. There's a combination of horizontal and vertical adding together in different parts of this interferogram. I don't think Gareth uses this particular interferogram for modeling because it's a little bit complicated to model. So
it's got 2 separate segments and a kind of an area of uplift between them.
Yeah, it's more challenging than some of the simpler earthquakes. But it's a good example of a Sentinel-1 interferogram because it's an area with very almost 0 vegetation, so the coherence is extremely high over the whole area. So as I was explaining, what is it? Not sure why it's doing this. Oh, this is showing the effects of the filtering. Yes. So this top interferogram is the topophase.flat merged interferogram before filtering, and the bottom one is the filt topophase.flat interferogram after filtering. So you can see that it becomes much smoother after the filtering. You can change the filter strength if you want. The default is 0.6. Sometimes for earthquakes, you want to reduce the amount of filtering. For the Ridgecrest earthquake, because the amount of deformation was very large, I actually had to reduce the filtering to basically almost no filtering, because right here near the fault where the fringes are very close together, after filtering it wiped out the fringes, and the phase unwrapping was no longer able to do the correct job. So that's something to think about when you're choosing a filtering, is that sometimes for earthquakes, less filtering works better. There's also this possibility of doing so now the next step is the phase unwrapping that you did manually this morning. We're going to use the snafu unwrapper for this interferogram. Yesterday we used the ICU unwrapper. The ICU unwrapper masks out the low coherence areas, and then it unwraps only the parts that have high the coherence above the threshold. But the snafu program unwraps everything, whether it's coherent or not. And that's something you have to be careful with, because sometimes well, though even in areas where there's basically no information, it's perfectly incoherent. Snafu will give you an answer. That it's not likely to be correct. With snafu, the snafu program what we normally do is the snafu program unwraps everything, and at the end it's going to create this connected components mask, as we explain a little in the next part of the cells here. And that connected components mask will provide the information about which areas are low coherence and therefore unlikely to be correct. And we can use that connected components mask to mask out the areas that are unreliable for the unwrapped phase. So that's done after the phase unwrapping normally. The snafu program that we have built into ISCE version 2 is snafu version 1.4 from about 10 years ago. The snafu author made a new version of snafu that's I think it's 2.1 or 2.2. And that's available for you to download from the Stanford snafu website, but it's not integrated into ISCE yet. I think some people are working on that, but it's not merged into the main version of ISCE 2. I believe ISCE 3 is using the newer version of snafu. If you want a fast unwrapping, generally the ICU unwrapper is the faster way to do the unwrapping. Well, it's almost always faster because it does mask out the areas of low coherence, and therefore not have to spend any time trying to unwrap those areas. In this particular scene, because the coherence is very high everywhere, the snafu is not spending any time trying to unwrap areas that are low coherence. So now it's already done. It's a relatively small area, so it's the unwrapping it didn't take so long. Now we can plot the unwrapped phase. This is the unwrapped interferogram in radar coordinates. For ISCE, we will be making these unwrapped interferograms in radar coordinates and releasing those in addition to the geocoded unwrapped interferograms. And on the second plot here is the connected components file. If you look very, very carefully, you'll see there's a few tiny little spots here that are places where there was a little area of low coherence that wasn't, where the phase was not connected to the rest of the interferogram. So you probably would want to mask those little points out if you were going to do a more advanced analysis. And most of this area is in connected component number 1. And those other connected components will have component number 1, 2, 3, 4, 5. The default is to only go up to component number 20. But that's one of the adjustable parameters. There's also another system called another option called the two-stage unwrapper. You have to install an extra piece of software that does this optimization for the two-stage unwrapper. We're not going to cover that today. And now we're ready to do the geocoding. So this is now that we have the radar, the unwrapped phase and radar coordinates, so we do the geocoding back in when we were forming when we did the merge bursts on the interferogram, it also did a merge bursts for the geometry file. So if we go back here to the InSAR geometry reference directory, there was both these geometries for each one of the bursts. Oh, no, I guess it only, no, it's here. It's under merged. So there's a new merged geometry file. That's these lat.rdr, lon.rdr, los.rdr, and z.rdr. So those are the merger of the geometry for each one of the bursts into, so that this is the geometry for the merged interferogram.
Eric, there's a question here about setting thresholds for correlation.
The SNAFU program that calculates it doesn't give you an option for changing the coherence for the connected components calculation. That's just the way the program author designed it to have a coherence threshold that's based on the number of looks that you've taken in the radar processing. For the ICU unwrapper, there's some options you can choose for what coherence threshold you want to use for unwrapping.
I was looking in the TOPS app XML file and I couldn't see the option.
It's not in the well, it's in there somewhere. I'm not sure exactly where. I mean, it's maybe not in the example XML file, but it is possible. So now it's geocoding the interferogram. Again, it's using 16 threads, but I'm sharing my machine with probably 2 or 3 of you other people, so it's running a little more slowly now.
Yeah, I don't know if we want to in future specify how many threads people can use, because that might be a problem.
It's first geocoded the phase sigma correlation. As I explained yesterday, there's the original correlation that's calculated from the unfiltered phase. That's the topo phase.core. And this phase phsig.core is the phase sigma correlation. That's the effective correlation that's discussed back here. Here. Phase-sig.core is calculated using this equation, the inverse of this equation. Oh, well, this equation. If we know what the sigma is, the phase sigma or phase variance, it's the sigma squared, the number of looks, and then we can calculate what the effective coherence is. This notebook doesn't actually plot the coherence. I guess Haresh doesn't pay attention to coherence as much as some people.
He's from Kurdistan, where it's all very dry.
Well, I've done a lot of work with coherence, and so has Paul Rosen. So that's why Paul had a whole notebook about coherence or correlation. I tend to call it coherence, but it's we're measuring with correlation. It's basically the same. I wrote a paper with Paul Rosen about the BAM earthquake coherence maps, because with the which explains a lot about how the correlation and coherence are related, and how we can use the coherence of the interferogram to show where the fault rupture is. And in additional, because buildings tend to be very coherent. The city of BAM was very coherent before the earthquake, and the coseismic interferogram, there was a huge decrease in coherence or correlation within the city. And by taking the difference between the pre-earthquake correlation map and the coseismic correlation map, we were able to get a coherence or correlation change map, which showed very well how much area of the city of BAM was destroyed. And in fact, I think like something like 70–80% of the buildings were destroyed, and something like a third of the population died. It was a horrible earthquake because the fault rupture was directly underneath the city. And then later, Sang-Ho Yoon at JPL took that method of taking the correlation difference as a way of measuring damage, and developed it into what he called the damage proxy map. And we now have been making damage proxy maps for a large number of events, earthquakes, landslides, tornadoes, hurricanes, explosions, like the unfortunate explosion in Beirut. We could see very clearly which part of the city was destroyed by the correlation change between the correlation for interferograms before the explosion and the correlation after that included the explosion. And that's turned into a very powerful technique for measuring damage by looking at the radar correlation. If you want to do that correlation differencing, you really want to use the real correlation. That's the topophase.core files, and not the effective correlation that's coming after filtering, because the filtering kind of destroys a lot of the information about the coherence. It's almost done. What's it doing now? It's doing the filtered unwrapped phase. People are asking about the height of ambiguity. The height of ambiguity is depending on the radar wavelength, and and that tells how long the baseline is before you get one fringe of in the interferogram. For C-band, with it also depends on the incidence angle somewhat. But for Sentinel-1, the height of ambiguity is something like 2,000 meters. I mean, the height of ambiguity depends on the baseline and the radar wavelength. So the Copernicus interferograms, most of the pairs are within 100 meters. That means that the height of ambiguity is around 2,000 meters. So you really need to have a huge amount of topography before you have a phase that needs to be subtracted. The way we do the processing in ICE, we don't actually, for the topo phase.int is already has the topographic phase removed. So we don't keep the, let's see, even the burst interferograms. Even these burst interferograms already have the topographic phase removed. So unlike some other software that first forms the interferogram and then calculates the topographic phase and removes it, because we're using the DEM earlier in the processing to do a better co-registration and calculating that offset field using the DEM, we already removed the topographic phase when we form the interferogram for TOPS app and StrictMap app. Okay, so I think it's finished. No, it's not quite finished. Almost finished. The old satellites, like especially ERS-1 and ERS-2, they let the satellites move around much more, like I think up to 2,000 meters. And the ALOS satellites even worse. They let the ALOS satellite move by 5 kilometers before they pushed it back to be where it started. So ALOS interferograms are actually quite complicated. You have to find out which pairs have reasonable baselines. Because if you have a 5,000 meter baseline, it's going to be incoherent no matter what you do. And the height of ambiguity could be like 2 meters. And then any DEM error would cause problems.
And it was biased, right? Because if you made sequential interferograms, the baseline was always increasing.
Yeah, they let the satellite just drift for, I think, 2.5 years, and then they pushed it back, and then it started drifting again. So that was just for ALOS, the first ALOS satellite. ALOS-2, they maintain the orbit quite small. ALOS-2 doesn't have any of that problems with ALOS-1, but ALOS-1, they wanted to save fuel by only doing this big baseline adjustment once during the mission. I think they realized that was not, I mean, ALOS-1 satellite was also a combined satellite that had both optical and radar data. So the optical people didn't care so much about the baselines, and they just let it get large. The ALOS-2 satellite was different. The ALOS-2 only has the radar instrument. They're about to launch ALOS 3. ALOS 3 is only optical instruments. And then they're also building ALOS 4. And ALOS 4 is again only radar. They realized that there's obviously advantages to having everything on one satellite, but there's also a lot of disadvantages. And they decided with ALOS 2, 3, and 4 to separate the radars from the optical instruments.
What's the orbital performance for ISAR? Do you know?
ISAR has a strict orbital distance of 200 meters. And it's supposed to stay within that. I think we usually, some people call it an orbital tube, as though it was a circular cylinder, but it's actually a parallelogram. And we actually, there's actually there's a whole group at JPL that's going to be working on the orbit determination and figuring out when to do orbit adjustments. But then they also have to work with the ISRO, because ISRO is the one that actually operates the satellite. So ISRO is actually doing the orbit maneuvers. But we're going to be working closely with JPL to do to design the orbit maneuvers to keep this 200 meter. It's sort of like a tube, but it's actually a rectangle or a parallelogram for the whole length of the mission. So that'll allow us to form interferograms from any pairs. The big difference with NISAR will be that we'll be acquiring data every 12 days everywhere. The ALOS satellite and ALOS 2 have a limited, even though ALOS 2 is only radar, it's not competing with optical instruments. The satellite was only able to collect data, I think, for 20 minutes out of the 90-minute orbit. And now the ALOS 2 satellite is getting old. It's been in orbit for 8 years. The batteries are getting a little bit degraded, and they're only allowing it to collect data about 10 minutes per orbit, I think, something like that. So the amount of ALOS 2 data being acquired is decreased in the last 2 years, since they are trying to conserve the fuel. They want to keep ALOS 2 operating until they can launch ALOS 4. They still are scheduling ALOS 4 to be launched in 2023, and we hope they get it launched soon. We're kind of in a race, I guess, to see whether we can launch NISAR first or ALOS 4 first. ALOS 4 is further ahead, so I think there's a good chance they're going to launch ALOS 4 before NISAR. And we've also been negotiating between NASA and JAXA to have NASA helping with the downlinking, bringing data down from the satellites. NASA has invested in a lot of new radar radio signal downlink stations. There's a huge new downlink station at ASF, and another one in Virginia they built an extra new dish at ASF, and another one in Virginia to handle the huge amount of data that's going to be coming from NISAR. But they're also going to be able to use that for other satellites, like ALOS 4. And I think they're still negotiating the exact terms of that, but the NASA requirement is that if it comes down through the NASA downlink station, then it has to be open, free and open data access to everybody. The NISAR data will all be free and open data access, and the ALOS 4 data that's downlinked through the NASA data network will also be free and open data access. What is the role of ISRO in NISAR? Well, there's a ISRO is building the core module of the spacecraft. They're going to be that has the solar panels and the rockets to control the orbit, and they're paying for they're going to use an ISRO rocket to launch ISAR, and they built the S-band radar instruments. There's a big radar radar assembly that's being it's here at JPL. It's being tested right now, or they're torture testing it, shaking it to like it's going to get shaken when it goes on the rocket. They've already installed all the L-band radar. So JPL built this big structure and the L-band radar, and ISRO built the S-band radar, and they brought their engineers over here to install the S-band radar panels and electronics and all that stuff together into this big radar assembly. JPL and a contracting company built the big boom and the reflector that's also connected to this radar assembly. And once all this this boom and assembly is tested, then we're going to ship that to India, and ISRO is going to connect it up to the core satellite and test it again, because obviously all that radar structure is just a lot of electronics. It has to get all of its power from the main part of the satellite, the core of the satellite, and the downlink antenna, I think, is connected to the main part of the satellite. So it's really a very highly integrated mission between both NASA and ISRO contributions. I'm not sure what it's doing here. Seems like it should have been done by now. It's now geocoding the wrapped phase interferogram. It previously geocoded the unwrapped phase. It also geocoded the line of sight vector. To do your modeling, you want to have that line of sight. LOS.RDR is in radar coordinates, but the LOS.RDR.geo means that it's been geocoded. So for your modeling use, you want to use this LOS.RDR.geo that has the look angle, look vector, incidence angle, and azimuth angle for every pixel in the geocoded coordinates. It also geocodes the wrapped interferogram.
Nearly there, though.
Yeah, I think they set up an option to have a special for instructors to have a special machine that wasn't shared with other people. I tried to use it the other day and it didn't work right, so I decided not to try it today.
We'll let Franz know when he gets off his plane.
Yeah, Franz decided to take a tour today. There's a NASA airplane that's in Fairbanks today. It has a radar that was built at JPL called UAVSAR. UAVSAR sounds like it would be on an uninhabited aerial vehicle, but it's actually on a piloted NASA airplane. Okay, so it's finally finished. Here's our geocoded unwrapped interferogram. This is one of these strike slip earthquakes with the side, the two sides went horizontally. There's a decrease in phase south of the fault and an increase in phase north of the fault. And that's a combination of the east-west horizontal motion and the vertical motion from this earthquake. So this is our geocoded unwrapped interferogram that we were spent this. So this is our final result. The rest of this notebook does some additional steps of how to discusses how you could use your own DEM. The default process is to do the geocoding with the same DEM that we use for the processing. We can look at the topsapp.xml file here, but you can actually specify a separate. That's the this DEM file that's specified here is the DEM for doing all the interferogram processing, but you can specify a separate DEM for geocoding. Because we're taking a fair number of looks here, the interferogram we're forming is 7 range looks is it's around 50 meter pixel size. So the DEM that we the SRTM data that we used for the main processing has 30 meter pixels. We might decide that we want to do the geocoding with 50 or 60 meter pixels, because we're to geocode at 30 meters means you're kind of oversampling the final interferogram. So you can specify your own a different DEM for geocoding than you used for the rest of the processing in the XML file. So this other step, this didn't work for me yesterday. I'm not sure what happened to it. There's a routine called downsample DEM. In this case, to downsample it for 120 meters pixel spacing. But it's not working. I didn't figure out why it didn't work. So we can also look at these files we can also convert them to GDAL formats. Oh no, this is GDAL to ISCE is for converting a DEM from like GeoTIFF to ISCE format. You want to have it in ISCE format to use with ISCE. There's this fixed image XML file. The ISCE XML files actually have the path to the DEM in the XML file. So if you move the DEM to a different place, then you need to run this fixed image XML command. There's also another whole section here about doing dense offsets. We're running out of time today, so we're not gonna. I'm going to start this running, but I'm not going to wait for it to finish. So dense offsets is we use the downsampling DEM. A lot of times if you want to do modeling, maybe you want to have your geocoded DEM with a larger pixels and degraded resolution. So that's what downsampling the DEM means, creating a coarser DEM. It starts to create this file called coarse DEM, but there's something wrong. It's not quite working. Probably it's because they had to adjust the different version to a different version of GDAL than different versions of GDAL do this step differently. So I think there's something wrong with it here. It's not that particular ISCE program isn't working in this OpenSAR Labs version. So especially if you're going to take more looks. In this case, we only took 7 range looks and 3 azimuth looks, but like the ARIA standard products are at 19 range looks and 7 azimuth looks, which is around 90 meters. So for that, then you're almost sure you ought to do your geocoding at 90-meter resolution and not end up with these huge files that don't actually have the. You want to make your geocoded output have roughly the same pixel size as your interferogram and radar coordinates, not oversampled. That's what the whole geocode, the geocode DEM file name is for changing in your XML file. And then dense offsets is doing cross correlation between the reference image and the sample secondary image. We do that to get the co-registration, the misregistration step in StripMap app. But when we do that for misregistration purposes, we do those calculations separated by 1,000 or 2,000 pixels. So just get an overview of the relative offset between the two images. But we can also do that in higher resolution. In fact, I'm just going to stop this and because I've already run this and skip straight to the viewing. So and this is taking the amplitude images and doing cross correlation between them. This is in radar coordinates. You can see that the basic offsets, can be quite noisy. In this case, the range offsets are actually, they're actually measuring the same type of the exact same geometry of deformation as the interferogram. It is in the same geometry. So this left side is this is the slant range of the image. And because the Sentinel-1 has very fine pixels in the range direction, they're 2.5 meter pixels, we can measure range offsets to around 20 centimeters. And so we can see a significant signal here, but it's also noisy. So there's a filtering step we can do. We also can calculate the azimuth offsets. That's the offsets in the along track direction. But the Sentinel-1 has a much coarser pixel size in the azimuth direction of 14 meters. And that means that we can only measure azimuth offsets to within around a meter or so. And this particular earthquake, because most of the deformation, the displacements are east-west, the azimuth offsets are basically zero. For other earthquakes, if there's a fault that's going more north-south, then it may have a lot more north-south motion and show a bigger azimuth offset. And we can filter it and display the filtered interferogram. After filtering, we can see this range. This is the geocoded filtered range offsets, and you can see it basically has the same pattern as the interferogram. It's measuring the surface displacements from the radar amplitude rather than the radar phase. That has a big advantage because it doesn't have the phase unwrapping, and it can measure very large deformation. We can use this technique to measure magnitude 8 earthquakes that have many tens of meters of displacement, where the fringes are not able to be unwrapped, but we can still get the very large deformation using the pixel offsets. So the range offset map is basically this in the same geometry as the interferogram, but with a much coarser precision, lower accuracy, but able to measure very large displacements.
Yeah, for glaciers, it's often like better than trying to do InSAR. Those
Yes, for glaciers that move, some of these glaciers that move meters per day move far too much to do interferograms. after filtering, the azimuth offsets here have basically no signal because this earthquake it was mostly east-west motion, and as I mentioned, because of the larger pixel size in the azimuth direction, we can only measure to within a meter, and there's much less than a meter of north-south deformation in this earthquake. So I think we're done with this notebook, and your homework for today is to finish this processing and try some of the other options if you get time. Like maybe process the other two subswaths, or do your own pair of Sentinel data.
Awesome, thanks. Maybe we should just look at the homework before we dismiss everyone. Do you have the syllabus up there? You just put it up.
Syllabus.
And maybe zoom in a bit.
Okay.
Yeah. So what we have for you to do today is to finish the exercise that we did this morning, or our morning anyway. Make sure that your profile is completed and make sure the questions are answered, and save the notebook with the answers and save the profile and post them to your homework folder. And then what we have as homework for this, and this may take some time and you might want to take a break before you do it, is to download a pair of images that you're interested in processing and from Sentinel-1 and run it through this notebook again and process your own interferogram. What I recommend you do is make a copy of the notebook, rename it something different before you do that, so that it's separate from the one you've just processed, and also maybe make a new folder to
put it in a different folder. Yeah, that would, you really want to put it in a different folder,
because this creates a load of different folders, that subfolders that it will use. So yeah.
One other thing that I forgot to mention that's important is that you don't have to do these notebooks. You don't have to run TOPS app or StripMap app as a bunch of separate steps like we do in this notebook. We do that to better explain what it's doing on all the steps. But we could have just run. We can run topsapp.py here without specifying the just with a dash steps, and then it'll go through all the steps without, if you don't specify a start step and an end step, it'll do all the steps. It'll take maybe an hour or 2 hours to run, depending on the size of the area that you ask for. But this notebook is set up to do all the steps as individual steps for better understanding. But in most cases, we just run the whole TOPS app with just the dash steps option that does all the steps together without stopping after each individual step. And I think that's it for the homework today. I want to do another example. If you have a favorite area that you want to look at, there's basically Sentinel-1 images available at the ASF from basically anywhere in the world. If your area of interest is in a tropical area, then you're going to want to use the shortest possible time interval, because otherwise it'll be completely incoherent. And the desert areas are always favorites for C-band interferometry.
Yeah, Southern California, the Middle East, favorite areas.
Yes, Turkey is pretty arid, not quite as dry as Southern California, but still quite good.
We look forward to seeing what you come up with.
Great. Thanks so much for coming here today.
Yeah, thanks everyone.
See you tomorrow.
Bye. Nate.